Friends, this is lecture number 55, basically the tutorial whatever we learned during this week. We are going to see some of the problems and the solutions related to hydrologic design, hydraulic design of the surface drainage system, and then cost and benefit ratio, whether the drainage project is economical or the drainage project is worth, that we are going to discuss in these examples. So, here as I said, this example number 1. So, the find a section dimension of drainage channel to carry runoff from 50 hectare watershed. This is watershed with a drainage coefficient of 5 liter per second per hectare. The average parameters are channel bed slope, that is S is equal to 0.2%, channel side slope Z is equal to 1, maximum permissible mean velocity, that is V is equal to 0.6 meter per second, and Manning's roughness coefficient N is equal to 0.025. So, in this the peak runoff rate is given, and Manning's N and other parameters are given. So, only thing is you have to find out the design parameters of particular channel, like what is breadth and what is width, what is top width and bottom width, all those things. Okay. So, let us see the design discharge, that is itself 5 liter per second, right, per hectare, and area 50, 50 hectares. So, the total will be like 250 LPS, like 0.25 meter cube per second. This is the capital Q. Okay. And the Manning's formula V equal to 1 by N R power 2 by 3 S per half. So, V is given 0.6, N is 0.2025, and S is 0.2%, that is 0.002, and only the unknown is R. So, the R you can get 0.6 is equal to 1.79 into R power 2 by 3. Okay. So, now you can find out R from this equation. So, R is equal to here 0.194. Okay. From continuity equation, Q is equal to A into V. So, where A is equal to Q by V, we know the Q value, right, and V is 0.6. Now, A is equal to 0.4167 meter square. So, now A is equal to BD plus ZD square. So, this is if you consider the channel as a trapezoidal channel. So, this is a B, okay, and so if this is the D, right. So, the BD, so this is the BD cross section, and FZD square, right, half ZD square plus half ZD square. So, that will be ZD square. Okay. So, this will be now because two triangles here. So, now substituting the values, A value 0.1467 and BD plus Z is 1, right, side slope, and D square. So, B is equal to a function of a D. Okay. So, now R is equal to A by P, we know, since R we know, A we know, right. So, the P like a perimeter. So, the perimeter will be what, this is a B, okay, and these lengths. So, it is a part of triangle, right. So, these lengths. So, that is 2D plus Z square plus 1, the square root. So, you get this is a P. Now, substituting values for B and A and R, right. So, you get the values like R is equal to, so putting the all values. So, R is equal to D and D, this is also D, right, substituting R value as 0.19407. So, this equation, this is a quadratic equation d square minus 1.1746 d plus 0.22796 equal to 0. So, it has two roots, right. So, one is d 0.9269 and 0.2477 meter. And now, let us substitute any one of these, let for example, b is equal to 0.9269 square, right. So, now sorry d is equal to, then you get b in negative term. So, then this is not the value. So, we have to take 0.2477. So, taking the point, substituting the d is equal to 0.2477, you get 0.2477, you get d b value 1.43 meter. Okay, so 24.8 centimeter is depth and the breadth is 1.43 meter. So, the flow area, so now the flow area, substitute the p value, that is the area perimeter. So, the perimeter will be BD plus ZD square, right. So, substituting that you get 0.416, that is the flow area. Then flow velocity, so that is q by A, right. So, you get the flow velocity 0.6 meter per second. According to the freeboard, such a 5% depth to be design depth, like freeboard you have to increase the freeboard because this is really important. When there is a siltation, the water level definitely rises. So, we need to accommodate that rise by giving the 5% freeboard. Generally for soil conservation structures it will go up to 20%. So, now depth d is equal to 24.8. So, let us considering the 5% freeboard like 26 centimeters, you can go up to 30 centimeters say. Now, top width of the construction BD plus ZD square, that is the top width. In the top width would be 0.149 meter square. Okay. This is the top width. Then the volume of earthwork per meter length of the drain for this construction will be 0.519 meter cube. So, this is per, like this is a 1 meter length. So, this is the floor a cross section, right, and then if you can put 1 meter length. So, the earthwork volume of earthwork will be 0.519 meter cube. Okay. So, this is example number 2. In this we are going to find out what is the discharge, what is the peak discharge. So, here the calculate the peak rate of runoff from 10-year recurrence interval from a drainage basin of 40 hectare area. The land is flat, so it varies from 0 to 5% slope, consists of cultivated clay soil. The maximum length of flow is 800 meter and the difference in elevation between the most remote point and outlet is 7.5 meter. So, assume rainfall intensity of 6.5 centimeter per hour. So, in our previous lecture, so for finding out the peak flow rate, so we have like rational method. Okay. In the rational method, so the basically runoff coefficient is one thing and time of concentration. So, once we know the time of concentration, that is duration, and knowing the return period, you can find out the intensity of rainfall, that is I, and area of watershed. So, Q is equal to CIA by 360, you get the peak flow rate from the particular watershed. So, here in order to find out TC, that is the time of concentration. So, the slope, it is given like H. So, that is the difference 7.5 meter most remote point to the outlet, and then the length of run L. So, you get this is the slope. So, knowing L and S, you get TC. Okay. So, TC will be 20.24 minute, and the next is the runoff coefficient C. So, giving values, if you see the cultivated land and the flat land, okay, and then clay soil. So, this will give C is equal to 0.5. So, C 0.5 and area we know 40 hectares. So, 0.5 into 65 is given, right, 65 what is it, mm per hour and 360. So, you get 1.3 into 10 power 4 meter cube per hour is the peak discharge from the particular 40 hectare watershed. And here example 3, so this is the drainage project economic evaluation. So, assuming an interest rate of 5.5%, this is interest rate, average cost for irrigation works 1125 per hectare, total drainage cost 875 per hectare, operation and maintenance cost, annual cost is 23.75 rupee per hectare. So, here the I mean the area has been distributed and the net benefits by land classes, right. So, here the for 96 hectares you may get annual benefits of 181.25, 40 hectare 156.5, 120 107.75. So, based on the classes 1 to second class. So, the classes are so based on soil group or the productivity, those classes, and the total annual benefits. So, the hectares multiplied by these annual benefit, you get 17,400, 6,260, that is 40 into 156.5. Then the total would be 36,590 is the total annual benefit from the particular land. So, so this is the total, but per hectare if you see, so the average annual benefit 36,592. So, 256 days basically we use for the what you call farming. So, that is why 256, and you get 100 142.93 per hectare. Okay. So, that is per hectare, and then sorry. So, this is the total area, 256 is the total area. So, this is the total annual benefit, okay, 36,590, and this is the area, total area. So, this is 256 and 142.93 per hectare. So, find an estimate of economic feasibility over 100-year life expectancy of the drainage system. So, you are asking what is the economic feasibility, whether the the worth to invest in this particular drainage project or not. So, for that the present worth, that is PW of capitalized average annual benefit. So, that is interest factor annual benefit. So, we know this equation from the previous lecture, and multiplied by the annual benefit. So, you get this is the factor, this is present worth factor multiplied by annual benefit. So, you get 22,586.4 per hectare is the present worth. So, that means benefits, the value of benefits in the present time. So, that will be 2,586, and then present worth of capitalized annual, this is cost, right, operation cost if you see. So, the same thing. So, 23.75 is given, and the present worth will be 429.78 per hectare. Okay. Now, the cost summary if you see. So, the drainage has some cost 875 per hectare, that is given, irrigation cost 1125 per hectare, operation maintenance 430 per hectare, the total is 2430 per hectare. So, benefit minus cost or benefit cost ratio. So, this is the benefit 2586. So, the present value we calculated, and this is the cost here 1.06. So, drainage project benefit cost ratio more than 1. So, it is considered as feasible. So, in this way in these projects, the drainage projects, So, knowing the and expectations in 10 years or 20 years time, so those are the benefits. So, those benefits would be bring to the present value by multiply with the discounting factor. So, then we will compare with the costs and see whether the present benefits are more than the cost. Okay. So, if they are more than the cost, then definitely it is worth to invest in the particular drainage project, and cost benefit ratio, like benefit by cost ratio, should be more than 1. So, these things are need to be studied before investing in drainage project. Okay. Thank you so much.